Good afternoon, everyone, ladies and gentlemen, who's joining us on site here. So after the lunch break, hope you had great discussions between the sections, and those who are joined us online, also welcoming you to our section regarding data. And the name of our topic is Shaping the Future of Research Through Healthcare Data. So throughout the sections yesterday and today, as well as in many news outlets and industrial talks, we have heard that healthcare data is called a new oil. Let's call it rather an oxygen that is filling the lungs of innovation. But we all know that healthcare data has a lot of potential, both hidden and unhidden value that we can apply towards new treatments or accelerating new drug treatment, diagnostics research, as well as helping those in need. But there are different challenges, both technical and technological challenges. So when data is being siloed across multiple institutions, often unstructured, not standardized, there is also legislation and regulation challenges that prohibits us or slows down the collaboration between multiple institutions in different countries worldwide. But how can we tackle such issues, and do we have any advancements or practical examples of such solutions utilizing the data, helping clinicians, researchers, industry, and for sure patients? We will be covering this during the section today. And we'll have a series of our presenters covering the practical aspects and approaches towards utilization, collection, processing, and analysis of data. Please join us as well. And of health data. So our section will be followed by a panel discussion with the public sector representatives talking about the regulations, the ecosystem as such, how we can build this and develop to help all of the stakeholders present here and also online. So I suggest we start. And actually, I also invite the audience here as well as online to ask questions. So we'll have some time for a short couple of questions, Q&A, after each of the talks. So I will welcome you're all on the stage, I'll welcome to present Yannick Metsalik, who's from Tallinn University of Technology. And he'll be talking about the approaches to secondary use of data from Saudi Arabia and neighboring country Estonia. Welcome. Applauses.
Thank you very much for having me, and thank you for the organizer for this very interesting event. I have had a chance to participate in e-health development, both on like micro level as a software developer, and also on like a macro level, architecting national level systems in a few countries, and being chief architect of Estonian e-health also. And for the software developer, it's always very important to add value to the client and understanding what the client needs. And on the national level, it's even more important because there is so much on stake. And if I'm thinking of, I'm learning, of course, myself, how physicians or practitioners are thinking or what they're doing in their everyday work, and also what researchers are needing from the healthcare data. So everybody knows that it's relatively easy to take records of patient data. So you can decide that I will record body weight of a patient or blood pressure of a patient, and they just take a small note. The question is, why did you do this activity in the first place? And why do you think that this body weight is needed? So basically, you follow some guidelines, and these guidelines can be related to many different processes. And the primary use of data is often that you enter this data into one document or in some field of your user interface, but actually you have to deliver the data into many more processes. And the current standardization work basically is focused on this digitalization of these processes, and we are creating more and more messages or document types which regulate what data we collect. including also the data that goes into the research systems. But when we come to the precision medicine, then of course we will have more consumers of the data. We have different algorithms, and again you need to add more data to the medical records, but how do you decide what data you need to enter? And that's a big challenge for data entry or data capture side, data provider side, because sometimes you have to overdo the data entry again and again to really get the data into the correct form. Let's look at some examples of this problem. So we have had a project in Saudi Arabia for developing master plan for national health data analytics. The system of Saudi Arabia is interesting in itself, healthcare system, that they have many sectors of healthcare. So the Ministry of Health is just dealing with like roughly 60% of healthcare. Then you have hospital system for the king's family, you have national guards healthcare system, you have Ministry of Defense healthcare system, Ministry of Interior healthcare system, some university hospitals, then there is a private sector, and then some of the big companies that you may be aware of have their own healthcare systems. And they all regulate, operate in their own sector internally. They all have like healthcare departments or healthcare organization management. And the problem of Saudi Arabian government was to get the data analytics streamlined. So you know the health status of, and also healthcare status of the full country. And when we analyzed the different sectors, we found very well-equipped, very well-digitalized hospitals. Like in Estonia, sometimes you can just dream of this level of digitalization that we saw in few of the hospitals. Like you can get all the dashboards, you can get all the KPIs, reports, you just can dream of, and everything is online, digital, running smoothly. But in order to integrate this information from the different verticals, Saudi Arabia has introduced like a second level of government. There is Saudi Health Council, which was the main customer for this project, and many other institutions. It's pretty typical also for other countries that there are different data consumers who want to see information about the healthcare system. And as you can imagine, this system works very simply. So it's ad hoc, so you create an Excel sheet with some fields, and you just send it to all these verticals, and they have to send it further to the primary healthcare centers or hospitals, and then you get the data back. And creating this national level health statistics takes like a few years in this form. Not mentioning all these legal problems of giving orders to different verticals and so on. So what the Saudi Arabian government decided to do was introducing health data exchange platforms, but it's not easy to introduce just as a technology. And even if you have designed important standards, they still don't work, all this data exchange. So this project really focused on deciding the governance model on top of this exchange platforms. And the governance model started with separating the roles of data providers and data consumers. So the data consumers were the existing organizations who typically directly accessed data providers, and bringing this central data management unit in between of these institutions. But the data management is not enough, so somebody has to also manage all the standards and design the data services. So the separate data analytics unit was also assigned in this governance model. So eventually we have steering, what was already in place, and we had the data standardization units, which were also already working, but now we just established this central body which manages the data flows between the providers and consumers, which increases the secondary use of the data, hopefully. Because these super hospitals who had these data systems in place, they said also that we can provide all the data what is needed, but government has to decide what data they need. And so there was no single client for this data feed. So this is how it was solved in Saudi Arabia. Let's go to Estonia. So in Estonia, we already have this. We have integration platforms. We have national electronic health records. So it should be fairly easy to access the data for the secondary use. So in Estonia, we had hospital network master plan project. And part of this project was also study of the information exchange capabilities of both hospitals, but we also added this other viewpoints of data use, like patient decisions, management decisions, public health and research decisions, healthcare policy decisions, and healthcare financing decisions. Because in a small country, you can't really allow these different verticals to hire lots of people to process their data and like build more disease registries or build more research registries. It's becomes really expensive. And so we analyzed these systems, and we still found that even if you have all this integration in place, you have all the standards in place which hospitals and like in Estonia, all healthcare institutions, regardless of the ownership, they have mandatory data sharing responsibility. But still, for the research purpose, for example, or for healthcare policy making or financing decisions, we have separate data integration or data standards. And this raises the question, what we can do differently? Why this Estonian health information system is not providing all the data for all the sectors? So basically, it only works for the clinical decisions. And also in clinical decision making, it works as a primary data exchange, not like the secondary exchange where you can make a decision support or use some AI, but you basically have the original data for the data provider. It's all structured, it's all nice, but what is the problem? Why you still maintain this expensive secondary capture of the same data? So we analyzed it further. We used a maturity model of information sharing from American think tank Mitre. And this maturity model is giving you this typical like 5-level graduation of different capabilities, and the capabilities were shared between technical process and governance domains. And so we estimated that mostly in Estonia we are above the level 2, which is expert-based level, and we are like approaching the level 3, which is standards-based level. In some cases we are even further, like on the goal-oriented level, like level 4. And here we see that the respondents to these focus groups and interviews were really worried about the data quality of the shared data. And if we look at the documents in national EHR, they all corresponding to the regulation, so that it's all looks correct, but still all the participants have problems with data quality. And this needs further investigation. And this is what we are planning to do, to understand how to improve the data quality. And that's basically the the challenge for us. So we know how to integrate systems, we know how to create standards, we know how to agree all the standards and make systems to share this information, but we still lack the data quality for the secondary use. So how to approach this issue? So basically we have real-world processes where the decisions are made. It's clinical, it's patient engagement, it's research, it's policy, and the real-world processes generate data. And we have to make a distinction between managed data, what they collect, and decision data, what they use for decision making. And then there's a data sharing. And one side is creating supply, another side is creating demand. And the research question is whether we map these two sides ad hoc, like in old times, like you send an Excel file and you get the answer back, or you just go and interview. That's ad hoc approach to collecting secondary data, and this is what often happens. The other thing is creating static standards. So you force through the legislation that everybody has to report to the cancer registry this kind of data, and to the tuberculosis registry this kind of data, and to the diabetes registry this kind of data. This enforces some quality on the standards, but is it enough for the secondary use for the precision medicine? And the problem is that the standardization is very slow. So if you want to experiment with new algorithms or some decision tools, then it takes a lot of time to get the data into the central registries through the static standards. So we need to be more dynamic, and now the question is how to feed the original data capture with the secondary data use needs. So basically we have to make some parts of the algorithms available to the data entry. So data entry can be coordinated from the demand side. So the decision data drives, the need for decision data drives the data capture. Then the system becomes more dynamic. And that's basically what we need to research. So yeah, thank you, and I will stop now here.
Thank you. Just a very, very quick question. So you've showed us an example from MENA region, like Saudi Arabia, and then switching to Baltics. So it's such a different countries and such a different regions from one perspective. But from another perspective, what were the common things to consider, within implementation of secondary health data use that we should be aware of, or we should pay extra attention to?
In both cases, basically the aim of the healthcare data use is the same. You have health indicators that you have to achieve. You have healthcare system efficiency and sustainability indicators and like this general human development indicators. So it's all, everywhere. That's the same problem. And the data systems need to really generate the data that you need to calculate this.
Thank you so much for the answer. Thank you once again. Applauses to Yannick. And I assume that we'll continue this discussion also afterwards, during the coffee break with the speaker, as well as during the panel discussion afterwards. So I would like, with no further ado, I would like to give a floor to Professor Martis Leja, so the director of the Institute of Clinical and Preventive Medicine, University of Latvia, head of Department of Research at Riga East University Hospital, who will be speaking about data collaborative on gastric cancer. So the floor is yours.
Yeah, thank you very much. And actually, I'm a bit turning the stage because the previous presentation was from the position of really the system development. I'm just giving completely to the user perspective, but we have always believed that Estonian data system for healthcare is perfect and no other improvements needed, but it still seems that it's also good for us to know that also in Estonia there would be some further developments required. But okay, that's not linked to the current presentation. So what I'm going to speak is on data collaborative, and since my background is gastroenterology and my topic is related to the stomach, problems. I have shown also the logo of the European Helicobacter and Microbiota Study Group here. So that is really the topic that is close to my heart, and the abbreviation of the acronym of the project that we have been developing is CARACOL. So those are briefly my conflict of interest statements. And what I'm going to speak on, I will touch briefly just from the clinician's point, the rationale, where we are with gastric cancer, why. I will touch also the EU guidelines, recommendations that have been also mentioned before today. And then really go deeper into the principles of data collaborative as well as EU data, open data platform GAIX, and how this potentially could be applied in our use case. And first of all, not to go deep into the issues, into the very medical issues, just to say that gastric cancer, if to be calculated in absolute numbers, that is decreasing in Europe, that is decreasing in Baltic states, and globally as well. But on the other side, since the population is increasing, at least in some parts of the world, since the population is aging, in absolute numbers, really we cannot wait until the disease will disappear by itself. And as a result, and that is a projection of from the GloboCan database, in the next 20 years, actually, the number of absolute cases is not going to decrease, but going to increase. And therefore, really in EU, in other parts of the world, really the prevention issues are addressed. And what is also important, that it's calculated that at least 30 to 40% of the gastric cancer cases could be prevented. So there is really the potential for the prevention. And just to have a very brief insight into the pathophysiology development of gastric cancer. And this pathology professor from United States, originally he's from Columbia, Pelayo, Korea, have postulated his cascade that is known as Korea's cascade related to gastric cancer development. And it is unique in the way that the first time he has postulated that was back in 1975, but it stands still for now. And at that stage, when he suggested this mechanism, it was really not known that the general or the principal inducer of the gastric cancer is actually bacteria. It is Helicobacter, but there are also other factors like lifestyle factors, and actually what this guy was planning also to use for prevention was the use of antioxidants for prevention. So there are different means of prevention, but just to illustrate the key thing is this bug here, and as well to identify those individuals that are going to progress, because actually 1 to 2% only of those that are infected with this microorganism are developing gastric cancer in lifetime. And that's the reason why indeed large data could help us. Yes, more than 90% are related to the Helicobacter, but Helicobacter is always not always the same. It could be more ugly or less ugly. There could be host genetic factors, there could be dietary factors and multiple other factors that are responsible. There could be even hereditary gastric cancer, but it is really very rare. So if we are speaking about prevention, it could be primary and secondary prevention, but when we are speaking about screening, so sometimes the terms are mixed up, we need to understand what we are screening for, whether we are screening for cancer itself, and indeed that is a program that is run in Japan and Korea, but not other countries globally, and it's not really considered to be cost-effective. effective, whether we are screening for precancerous lesions, and there could be a couple of different possibilities, or we are screening for the microorganism, but it is not considered immediately as precancerous lesions. So if we screen for the bacteria, then we are just intending to give the treatment to those that are infected, and I would say immediately that this is a strategy that will be recommended in Europe for the future. If we are screening for precancerous lesions, there could be different approaches, and cancer, this is endoscopy, but that is not feasible definitely for Europe. So what is new in Europe currently? And the new European Council recommendations have been already mentioned. They have been published just a couple of weeks ago, but still this is a proposal. This has to be approved by the member states. And when it is approved, then we do have 3 existing cancers in where the screening is recommended. Just to remind, it is breast, cervical, and colorectal. But there are 3 new types of cancer that are really included in those recommendations, but still with the condition that the usefulness has to be evaluated, and what has been debated already in respect to the lung cancer previously. So it is lung cancer, it's prostate cancer, and gastric cancer. And what the guidelines or those recommendations are going to say, that Helicobacter screening should be considered in countries and regions with high gastric cancer incidence. And actually the Baltic states are among or the top highest incidence countries in the EU. And then also that the identification and surveillance of patients with precancerous lesions should be considered. So that is where we have started, and where we thought that really data, large data collections would really be very useful. And for that purpose, and we have been approached by the Microsoft company a couple of years ago already, and we collectively developed this concept on the healthcare data collaborative, meaning bringing together all the stakeholders, the industry, the research potential, also patients, to develop a strategy that is valued as a public health value, and that we have been using gastric cancer and precancerous lesions as this use case. So for what reason? Why do we need this? And there are a number of questions that still have to be addressed. And actually, we do not have the recommendations currently at the EU level, and the Commission is really expecting this. So first, we need to understand not only the benefits, but also the harms of screening, and for this broad-scale implementation research is required. Second, so there might be not everybody could be really similar. There could be more complex mechanisms of estimating and considering the risk, really to invite those that really need this for surveillance, investigations, or even treatment. I didn't have the time mentioning, but autoimmunity is one of the aspects that is also emerging. Then actually what we recognize that the quality of endoscopic investigations is very different in Asia, and they are using this method for screening, from what is considered as a standard in the Western world. And actually we expect that the artificial intelligence, when coming into this segment, could be really of help to improve the endoscopy, in particular in Western part of the world. Further on, digital pathology could be really one of the ways and one of the approaches to go. It is emerging in many disciplines, but also in this area, and this we are planning to address in a new project that will be starting soon. And also, furthermore, there could be different new approaches, not traditional approaches, very unusual approaches, like, for instance, testing for cancer from the human breast. So that is one of the approaches we have been using, and I will just demonstrate it very briefly. So the GAIA-X platform has been considered for the possibility to go this way. So what is a GAIA-X? It is really the pan-European initiative to bring together the digital ecosystem to the clinical sites, involving all the experts to have really the data available on a broad scale from different areas within Europe. It is decentralized process, and it should be really transparent and involving really multiple technologies and multiple stakeholders. So how it could help? And those are a couple of illustrations taken not from this project, but from publications. First of all, endoscopy, artificial intelligence in endoscopy. We do have commercial products already on the market for investigation of bowel, but we do not have so far for investigation of the stomach. And this is the area that is led by our Portuguese colleagues, and we expect really that products will come even to the market within a couple of upcoming years. Furthermore, artificial intelligence in pathology, what I have been mentioning, for risk stratification, we need really complicated, quite expensive, and maybe even toxic staining methods. If the same could be achieved by artificial intelligence from normal standard slides, that would be really a great achievement. And finally, just to illustrate, those are the data that are coming from the breath analyzers if you are using sensors for the purpose. I could imagine that nobody of you can read those curves. I cannot as well. So it should be really a large part of AI to be imputed there to really calculate and estimate what really could be considered pathology or not. That is not yet in place. This is a future, but there is a good possibility, and this instrument, what I'm currently demonstrating, is coming from a collaborative project with the acronym VOGAS that was just finalized the previous month, and still the results are under the analysis. So this is an ecosystem, how we see this for the GAIX, this application or data collaborative in Europe, and that was a project that we have developed together with multiple partners from different countries. There could be more than this, but it is involving not only research institutions as mentioned, but many others, including Microsoft, has been part of this general ecosystem. More than this, actually, this could facilitate collaboration not only in Europe, but also across the continents. And I drew here Chile, what is part actually of the Latin American group working on this topic. And this is not artificial, this is not because of the big distance, just to have a nice illustration. The reason for this is that Chile is going to run a very similar project to what we are planning in Europe, and that could be a high achievement to put those together. I'm happy to tell that just a couple of days ago, this Caracol project has been officially published on the web page of GAIX domain. So now it is formal. It doesn't give any funding, but really we are ready to start off and really to demonstrate how this could hopefully work. With this, I'm happy to finish and happy to take questions. Thanks.
Taking respect of the time, Professor, I suggest that we take questions during this, quick fireside chat afterwards. And it's quite interesting that we're moving from a federated approach in gastric cancer, not only towards the use case of federated learning from the next speaker. And I would like to welcome on stage Nicholas Probel, who is a doctoral researcher, Institute of Computational Systems Biology at the University of Hamburg from Germany. He'll be talking about the privacy-aware microbiome profiling for colorectal cancer detection using the federated learning approach. Let's welcome him with a round of applause.
Thank you. Thanks for the nice words. Privacy-aware microbiome profiling for colorectal cancer detection using federated learning. I know, quite a mouthful. So let's try and digest what we hear in this title. So, as we have just seen, machine learning has a great applications in many different fields, and Precision medicine is obviously one of them. And there are a few good reasons for this, and one of the reasons is the possibility to include a great amount of different data from different origins. And this data can be more classical in the sense of data related to the disease, treatment, or general healthcare data like treatment history. But this can also be a little bit more modern data like omics data or even lifestyle data or nutritious data. And using this combination of data set that can be extended arbitrarily, you can gain various different functions from this artificial intelligence. And those can be of more of an assistance-based type, like for example imaging assistance, right, during surgery, but also decision support or more predictive functions like risk modeling or early detection. And in this study, we wanted to show the application of federated machine learning on one special set of data, namely on the gut microbiome, which has also been proven to show great promise in treating various diseases, not only focused on gastrointestinal diseases, but also diseases like the autism spectrum disorder or metabolic diseases or even cancer immunotherapy. And in this talk, we want to focus on the last one of the few mentioned categories of diseases, the gastrointestinal diseases, namely on colorectal cancer. And one of those treatment types that showed great promise so far has been the fecal transplant, but this is not only the one treatment that works. So let's continue. What's the usual way you would do a data analysis, right, or collaborative data analysis? The first step usually is to put the data in one place, right? Okay, step 0 would be going to a conference and asking people who has some samples, right? We've heard this in the hallways. What you would do is you put all the data into one place. Here in this case it's the cloud, and while the cloud sounds like this untouchable thing that just floats around, right? It's not, it's just someone else's computer. So you're not only trusting all your partners in research and that they handle your data responsibly, but you also need to trust the entity that stores the data. And here you can see 3 hospitals, each sharing their respective blob of patient data. And when you do this, one thing is of central importance, and this is data quality. Here you can see a plot of the evaluation of a artificial intelligence. On the y-axis you can see the AUC, the area under the curve. This is a performance measure for artificial intelligence, and on the x-axis you can see the increasing amount of features, so in this case species used in the analysis. And as you can see, there are some data sets that perform quite well. An AUC of 1 is considered perfect or very good, and an AUC of 0.5, so the bottom is considered not very good or random. And we can see that most data sets perform quite well, and there are some data sets like this pink one that needs a little bit of a head start, right? It doesn't work with low samples, but a low number of features, but it works quite well afterwards. But there are also data sets that don't work well at all, right? Like this teal data set that just has low quality or other reasons why this is not helpful in predictive performance. So why are we not doing this right? We've heard this also during this conference a lot. It's the GDPR and various other data protection regulations. Those data protection regulations are very important. They are essential to keeping patient data private, as it should be, but it also hinders collaborative research. And if this is intended or not, we still have to deal with this, right? And in my opinion, one of the most important part of GDPR is the sentence right here: patients can revoke the consent at any time. So even if you manage to have a collaborative research, right, you share your data, you put this somewhere, give it to a partner. If a patient that is in your data set comes to you and wants to be removed from the data set, it's your responsibility to actually make this happen. And depending on how long this analysis ago was performed, are you still aware where the data is, who is currently handling it, and so on. And so quickly it happens that you lose track of data and can no longer guarantee patient privacy. So ideally, patient data should not leave the hospitals at all. This is one of the easier way to guarantees that you stay in control of this whole process. How can we do this? There is actually a way to do this. This process is called federated learning, and it's based on a very, very simple principle. So while previously you used to collect all the data, what you do here is each individual hospital, you can see 3 hospitals, each one trains their own artificial intelligence, which then get combined to a central, good performing big artificial intelligence. You could also imagine this in a different way, right? You can imagine this as a traveling artificial intelligence that goes from hospital to hospital, learning along the way without actually exposing any of the individual hospitals' data to the other participants in this federated workflow. And this was a little bit abstract. Let's continue with a more concrete example, right? This is a conventional linear regression. You can see 4 different hospitals at the bottom. Each one has their own data set represented by the small colored points. And what you would do in a conventional analysis, you would put all of this data in one place. In this case, it's a cloud. You can see there are a lot of different colored data points in the cloud. And then you would perform the analysis, in this case linear regression. You want to draw a trend line to all the data. And as you can see, great, you do this, but this of course is not privacy preserving. You expose all of your data to every participant in this workflow. And then there's the federated way of doing this. So this is a federated linear regression which is fully privacy preserving. As you can see, there are no longer colored points in the cloud. The colored points, the data stay in the hospitals, and you can actually see each hospital draws their own little line and just transmit the parameters it needs to actually show what line they drew to the central instance, to the cloud or whatever you want to use, right? So in this case, you all paid attention to school. To describe a line, you just need the slope and the y-intercept. So each hospital transmits the data, and you can see there are a few lines in the cloud, and by the end you can calculate the one performance combining all the individual data sets. And this is fully privacy preserving, and you mathematically end up at the exact same solution. And this is possible for a few of the simpler machine learning models to actually prove that this is equivalent. And for the more complex, it's not yet proven for some of them, but the performance is very, very similar, as you will see in a second. Great. So when is this happening? This actually is out there right now. We developed a platform called Feature Cloud. So a cloud that just stores the features. That is very user-friendly and allows you to execute federated workflows and federated apps that are prepared for you. We have some recent publications of federated genome-wide association study, a federated Limmer-Womb pipeline, so federated differential expression analysis, and federated survival analysis. Those are just a few of the apps that you can use for free. It's open access, everyone can use it, but there are in total over 50 machine learning applications that are already in there, and you are free to use. But even if you encounter the case that whatever method you want to use is not in there yet, we also made it very easy for anyone who can do this on a local machine, so every computer scientist who can program a not federated machine learning application can actually easily do this in a federated way. And to prove this, we held a hackathon at the beginning of the year, inviting 16 people from 8 different countries from all over the world who had no experience at all in federated learning, and we tried to teach them how to do this. And yes, most after 1 and all of them after 2 days were able to create their own federated application that they programmed themselves from scratch using the Feature Cloud platform. So now let's put this together. We are working with a French-German cooperation. The German part is called FEMI, Federated Microbiome Artificial Intelligence. And the German part is the Computational Systems Biology chair of the University of Hamburg, also called COSI Bio, headed by Jan Baumbach. And our French partners, the microbiome specialists, are Metagenopoulos in RAE, headed by Mathieu Almeida, who was also here at this conference yesterday, but sadly he couldn't make it to this talk. So overall, what they put together is a data set combining 11 publicly available studies, which have also been recently published as one whole data set. And this in total, after some pre-processing, means we can perform this analysis with 1,300 whole genome sequencing samples with 600 cases of colorectal cancer and 700 controls. This data includes taxonomic, functional, and demographic data like gender, BMI, age, and also, of course, the medical data, the result of the performed colonoscopy to actually determine if colorectal cancer is present. And we will test this analysis data set in two different scenarios. First, there is an easy scenario, and then there's a harder scenario. The easy scenario is the one on the left, the homogeneous data scenario. In this case, all of the different hospitals are similar to each other, right? They have a similar distribution of features like gender or the prevalence of healthy and sick in the data set. It doesn't have to be 50-50, it just has to be comparable to each other between the hospitals. And on the other hand, we have the more difficult scenario, which is sadly closer to real life. We have heterogeneous data, which means hospitals are very, very dissimilar to each other, some having great difference between, for example, gender. In this case, we have 75% males and 25% females, and in the next hospital, it's the other way around. We have 25% and 75% females. And this has been done for various amount of data. Various amount of features. So now let me quickly explain the figure I'm about to show you. So this on the left one is the small version of the figure you're about to see. On the y-axis you can see the accuracy, so the performance measure of the artificial intelligence we're using, and on the x-axis you can see the number of hospitals. So we simulated a number of artificial cohorts to show the feasibility to do this with 2 to 15 participants in a federated workflow. And on top you can see a red line. This is the central reference performance. So what happened if you would put all the data together in one place and do the analysis that way? This is our goal we want to reach. And then in the end we have two boxes. The orange one represents the federated workflow, so all the hospitals working together in a fully privacy-preserving way. And the blue ones representing the individual performance of the hospitals. And this is evaluated in a cross-validated fashion, which means we train on one hospital, so we created an artificial intelligence based on the data of one hospital and then try to predict the prevalence of colorectal cancer on all of the other hospitals. And we do this for every combination. Great. So now let's jump into the actual results. This is the results for the homogeneous data set. We can see the red line is at about 84% accuracy. And as you can also see, the orange boxes are quite close to what we would expect in a centralized, not privacy-preserving fashion. While when using only the hospitals themselves, so that every hospital not sharing, not working together, the blue bars, we can see the performance is quite low. Remember, we have two binary classification, so two classes, sick or healthy. So 50% is guessing, right? And guessing is not what you want to be doing when talking about cancer. And since we have a little bit more, so there's a slight imbalance in the number of healthy people, actually closer to 60% is guessing. So we can see if every hospital stays by itself and then tries to use the individual models they trained on other hospitals, they're basically guessing, and this is not what you want. And overall, this means we have a federated performance of 83.1% accuracy and an individual performance of 59.7%. And to remember, the central performance is 84%, so we are quite close. Now let's look at a more difficult example to see one of the advantages of federated learning. We can see that the blue bars actually changed a little bit. They actually went even worse, even further down, which means if you have bad luck and you happen to test the model you trained on a hospital that is very dissimilar to yours, the performance is even worse, even reaching below the 50%, which means actively guessing the wrong way, which is even less what you want to do, while the federated performance stays very constant around the performance of the centralized model. One small thing, as you can see, the left side dips a little bit, also on the previous slide. This is just a technical thing to keep the models comparable. We used the same hyperparameters, so they had the same training parameters for all the different analyses we performed, because we didn't want to do a hyperparameter optimization, so which is what you would do in a real-world scenario to really optimize every single percent point. But since we wanted to keep this comparable, we wanted to keep the same parameters. So what you would expect in a real-life scenario is actually those two boxes to be a little bit higher. And to be fair, probably also those to be maybe a little bit higher, but not too much. Great. So yeah, to wrap this up and even give a little bit of an outlook what is planned, We are trying to move this to a clinical scenario, namely the colorectal screening. And this is what is happening right now. We have often a fit-based colorectal screening, which has an a false positive rate of up to 37%, which leads to many, many unnecessary colonoscopies, which are, to be honest, not the most pleasant of experiences, right? So we even see that people are less willing to actually undergo this colonoscopy because they assume that it's probably a false positive, right? And also on the right side, regarding the microbiome analysis, even if you have willing participants who actually want to work together, we see that they actually can't do this, right? They can't find a way to create a centralized data warehouse or to get the data together. So with our proposed microbiome-based COC screening, we aim to reduce the false positive rate to below 17%, resulting in much fewer unnecessary colonoscopies, and also using the federated microbiome analysis, which is privacy preserving, because each participant keeps the data all by themselves, no data leaves the hospital, and also big data driven, since you have the predictive performance of having a lot more data, you can actually work together in a federated way, not only inside a country, but across country and even continent borders, to actually achieve a privacy preserving artificial intelligence that can make strong predictions and actually try to save lives with early detection of colorectal cancer. Great. And the last things I want to do is just say thank you to the team of Metagenopolis in Rae and Cozy Bio, and of course, thanks to you. Thanks for your attention, and please check out Feature Cloud. It's completely open access, and please start collaborating. Thank you.
So thank you so much, Nicholas. Please have a seat. We will have a really fireside chat for 7 minutes that we have left. Thank you so much. Please have a seat with the panelists. So meanwhile, I suggest that we catch Nicholas on a coffee break and spend our Friday evening not just having a relaxation time, but rather building a federated model prototype that he was referring to. And thanks for this new term, microbe AI ohm. I think it's quite good. Let's use it. So I will not let you rest just with the first fireside question from my side. And meanwhile, if you have any questions, please raise your hand and come to the mic. So federated learning, Nicholas, federated learning sounds like a silver bullet from your presentation. How cool is that? Super good results of training AI models, data, privacy preserving models, so everything is good. So my provocative question is what are the limitations, limiting factors of having this across all of the hospitals? Because it sounds like we all need this.
So there are two main problems. First of all, it's hard to implement, right? So it's just a computer science problem. So with Feature Cloud, we try to take this away and make it as easy as possible to actually implement this. And the other problem we have is, of course, data harmonization, because a lot of hospitals use different data standards. And we try to, with our proposed screening, we try to base everything on the FIRE HL7 ontology, which is very nice to use in a clinical environment and incorporates a lot of clinical variables.
Okay. So coming to Yannick, so just Nicholas just mentioned the ontologies that are set there. So my question is, standardization might sound easy. Basically, we have it on the table, am I right? So HL7, FHIR, lowing standards, etc., etc. So what is the challenge? Why can't we input it in the middle layer or in the base layer to make it happen?
Yeah, meanwhile, listening to the other presentations, I was also thinking that all the pieces are in place, actually. That we have new algorithms for diagnostics, we have federated AI, and what we need is to improve the data quality in these local systems. And in order to improve it, we need to communicate the algorithm back to the end user to know that this is the case where we need this data because of this AI algorithm. And so we need to assist the end users to really provide the good quality data in the first place. And this is missing. These guidelines are very static today. And these physicians just need to know that this patient needs this data. But maybe this AI could communicate it then dynamically to the end user that this case is going to this direction, needs this additional data, and maybe some lab test or some sequencing and these kind of things.
Please.
Yeah, if I may, I had also a question actually to you, and definitely federated data seems very good. The question is whether this approach is solving the issues of GDPR completely, because anyhow you are requesting the data from the different individual sites. So aren't there any issues with GDPR anyhow?
So no, we have obviously we have a legal team in the project, and they are working very hard to make this fully GDPR compliant. And using federated learning, you're not sharing any of the data you have. So as long as you have access and patient consent to use this data in this type of analysis, you are free to use this in a federated environment. And it's actually very hard to impossible to recreate some of the input data by just looking at the output artificial intelligence.
So we have a question from the audience. Please introduce yourself. I think we can hear you. Try again.
You can hear me? Great. I had a question. My name is David Friedman. I'm from Biomedical Research and Study Center. And I was curious, Janek, have you considered that the issue is not the data quality as such, but that people are more afraid that their data quality is different from that other group's data quality? You know? It's essentially, if you look at the numbers, the quality is the same, but the data might not be compatible because these errors which are within the measurements are a bit different. And then the standardization is actually needed to kind of, you know, put together so that they can find a middle point.
So if I understood, the question is what kind of data policy we need?
I mean, you were talking about standardization of how people do these things, but if you use two different machines in two different organizations, they have two different types of technologies within them, most probably. So the errors are different in essence. Mm-hmm. And the people, they are usually probably not that worried about the quality as such. They are quite sure that that other group has also very high quality data, but that the errors that they have within their data is different than ours, and that the data are not going to be compatible. You know, you can't put them together so easily because there's just bias because of the site where you got them from.
Mm-hmm. But as I understand, the question is that we have the heterogeneous network of different systems, and the standards are just taking us so far, so we still maintain the difference. And
this is what the people are worried about mostly when they're saying that we are worried about the quality of the data from that other group.
Yeah, but this is exactly what has to be solved also. So we have to solve the technical interoperability. So basically we have internet, we have secure connectivity. Then we have to solve the syntactic interoperability where we understand the information that travels between the systems. But then only then we can start thinking of composing integrated processes, so that the demand and supply side can communicate and agree what kind of information is needed in certain case. If we stay on this second level of just synthetic interoperability, then we have only information for the primary use of data. So somebody fills in these fields which are required by this standard, but the overall flow of information is maybe disconnected in some cases. So that's basically what we have to move in Estonia to standardize also the composition of processes that travel through the many different organizations. But the heterogeneity of the landscape of systems, that's a different discussion altogether, because the thing is that, of course, it's easy to dream that like one country like Latvia should have just one medical information system, and then all the problems would be solved. But unfortunately, we still keep the same problem of process composability, because the healthcare is not starting inside healthcare and not ending inside healthcare. So we have to bring social care, we have to bring financing, we have to bring policy making and different research and so on. So anyway, we need the process composition, we need to communicate what data we need from the data capture side, and then we can streamline the digital process.
Thank you for the question. I suppose we can continue this and supporting this with a cup of coffee. Before we finish the next panel discussion, the joint session with the ministries, of the Republic of Latvia will be about, policy making, about governance, etc. So from the panelists and the speakers, very short call to action or provocative question that should be addressed during the panel discussion from your side. What do you think should be asked or answered by the next panelists? Professor, maybe you can start.
Yeah, thanks. Actually, my question and my suggestion, we need to work together indeed, and there are possibilities of really what we heard today of joint activities. I think it would be very important really from the ministries, from the responsible people to really make the decisions so that those collaborations are much stimulated, that the available European funding sources are available, and to use them properly, that would be already the question of scientists and well-written application.
Thank you so much.
Yeah, I believe my question is very straightforward, right? So why are we focusing on centralizing the data and not on federating the data? Because everything is there that we need.
Perfect. Yannick?
I think this the overall idea from my perspective is to increase the value of collected data, and so the cost-benefit issue should be understood really on the top level of strategic thinking, so that the data is single captured and multi-used.
Thank you so much, dear audience, and those who joined us online, and see you like in 10 minutes after the coffee break. Let's have a round of applause for all the speakers.